This is the problem about the lake, and it says a 0.30 meter thick sheet of ice covers a lake. The air temperature at the ice surface is negative 15 degrees Celsius. In 5 minutes, the ice thickens by a small amount. Assume that no heat flows from the ground below into the water and that the added ice is very thin compared to the 0.30 meters. Find the number of millimeters by which the ice thickens. I think they're saying in here that the added ice is very thin compared to the original 0.30 meters, because once you add a few millimeters to that, you actually increase the insulation distance, and so that would change the problem slightly. So I say, it's very thin, and let's just deal with the 0.30 meters. Okay, this is all I could find, so obviously there's no ice on this lake, but I can make myself a drawing kind of in a cross section. So if I take here, let's say the shape of the lake, and then I put the water surface here, and then here's the water, and now I'm going to put a layer of ice on top. I'm not exactly sure I'm going to do that. Let's see, maybe some kind of off-white. Oh boy, this is going to be tough. It's going to be interesting. Let's see what happens. Yeah, something like that maybe. So there we go, there's the thin layer of ice. And now I would have to say that, changing colors, that here I have the negative 15 degrees Celsius, and then inside the lake here, just right underneath the ice, is 0 degrees Celsius, water. And of course, because there's a colder temperature here, heat will flow out of the water just beneath the ice, flow through the ice into the ambient air, and therefore this here will lose heat, and that water, that liquid water, then will become solid ice, and so it makes a phase change still at the same temperature of 0 degrees Celsius. So inside the ice here you actually have a temperature layering here with the coldest negative 15 on the top and 0 at the bottom of the ice sheet, and then 0 degree water, and then due to the density of water peaking out at 4 degrees Celsius, you actually have layers of 1, 2, 3, and 4 degrees Celsius. So inside a lake that is frozen over, you still have water at the bottom and it's 4 degrees Celsius. By the way, on a lake that is not frozen over, like this one here, you also have the 4 degree Celsius layer at the bottom, and then just the warmer water instead on top of it. Okay, I just recorded without actually recording. So I wrote this stuff down here and just talked into microphone with actually not recording. So what I wrote here is that the L is given in the problem as 0.3 meters. The temperature difference from the top of the ice to the bottom of the ice is the 15 Celsius degrees. The time T is given as, let's see, 5 minutes, I believe it's said. Yeah, 5 minutes, which will be then 300 seconds. And then we're supposed to figure out by how much the ice thickens. And then, of course, when I look at these here, that kind of gets me to the equation for heat conductivity. And then I notice there's an A. They don't tell us how big the ice sheet, how big the lake is. So I'm writing this down here without a check mark, but I'm figuring out that somehow it will divide out. We'll see. The K here, of course, is given. That's the conductivity of the ice. Okay, and then pretty much in this equation, yeah, we don't know what the area A is, and they don't tell us what the heat flow is. So we have two variables with one equation, and we really can't do anything at this point. But of course, overall, we're supposed to figure out by how much ice is being produced at the bottom, and that kind of leads us to the second equation. that means that, well, that liquid water becomes solid ice with a certain thickness. And that, of course, involves the latent heat of fusion for water. And so that is Q times L F times mass, with the LF, of course, given. I'm going to write this over here. Kind of run out of space with my little box. So the latent heat of fusion for water is given, but again the mass isn't given. Well, let's see what's going to happen here in a moment. And of course the variable d is actually not in here. We can reason that these two here will be the same. The heat flow through the ice is the heat that is taken away from a certain amount of water that then will freeze due to the latent heat of fusion. Okay, how do we get the d in there? Well, notice that the A here is not given, but it kind of gives us the area of the lake here, the area of the ice sheet, and the M, the mass, is not given, which of course is kind of similar to that. You know, the area of the lake or of the ice sheet times the thickness that will actually freeze times the density of the water. Well, there it is. So the mass here is the density of the water times the area of the lake times, or the ice sheet, times the thickness that will freeze now. And when you look at these here, at this one and at this one, that's what I said earlier, probably the area A is going to divide out. So I'm going to set these two equal. So the heat that flows out of a certain amount of water will flow, is the same as the amount that actually flows through the ice sheet, and because it has this much less heat available, it will undergo a phase change. So it, from liquid water at 0 degrees Celsius, it will become solid ice at 0 degrees Celsius. So setting these two equal is then going to look like this: Ka delta T divided by L. This is the thickness of the ice sheet, while the LF here is the latent heat of fusion, and then times the mass, which by now is the density of water times the area times the thickness of the new ice. And then actually I have to take something back. The density is actually the density of the new formed ice, which is appreciably smaller than that of the liquid water. So that mass here could be the density of the water times the area times the thickness of the liquid water, but that mass then would be the same as saying that this is the density of the solid ice times the same area times the actual thickness of the ice that we're supposed to figure out. So this one actually is the density of the ice, and then we're supposed to figure out what the thickness is with the area dividing out, and this is going to be a long one. So K delta T times T divided by LF and the density rho.